Question number 5 is a practice for you to use the terms hyper, hypo, isoosmotic as a comparison between two solutions. The first step you need to do is to obtain the osmolarity of each one of the solution that you are comparing. For example, solution C, the question only gives you the molarity, which is 1 molar of NaCl. For the solution, you need to convert the molarity into osmolarity first before you can make the solution, before you can make the comparison. Okay, so solution A has an osmolarity of 2 osmolar. Solution B is 1 osmolar. Solution C is 2 osmolar. You don't have to care about what type of solution it is, what type of solute there are in the solutions. You can simply compare their values of osmolarities to fill in the blank. Whichever has a higher number of osmolarity, it is all hyperosmotic. The one that has a lower osmolarity is the side that's called hypoosmotic. If they have the same osmolarity value, then they're called isoosmotic to each other. Note that if you use a different dissociation constant other than 2 in this question, then probably you'll have a lower than 2 value for this blank too. Then you'll have different answers than what I'm having here. For example, if you use 1.8 as a dissociation constant for NaCl solutions, solution C will have an osmolarity of 1.8 osmolar. Then solution A should be hyperosmotic to C. Solution B will be still hypoosmotic to C. And solution C will be hypoosmotic to A. Solution C will be still hyperosmotic to B. That's question number 5. There's another question number 5 in a workshop. That's 4 definitions. I'll leave the answer here for you to review on your own. I won't go over that in this video. Question number 6 are composed of 4 true or false questions. Let's look at them one by one. First one, if glucose concentrations in solution A and solution B separated by a semipermeable membrane are the same, the net movement of water will be 0. I say that is true because solution A and B has the same osmolarity, so they are isoosmotic to each other. There's no net water movement. There's no osmosis happening between these two solutions. Question B. If glucose concentration in solution A is half that of solution B, twice as much water will leave solution A compared to that from solution B. I say that this statement is true, but only at the beginning. Since both solution A and B are composed of the solute of glucose, a single solute of glucose, if they have the same concentration, they have the same osmolarity. So since glucose concentration in A is half of the solution B, then osmolarity of A is half of osmolarity of B. So the osmotic pressure in A is also half of solution B. So at the beginning, twice as much water will leave from A to B. Since osmotic pressure is the driving force of net water movement, so at least at the beginning, twice as much force will be applied to the water that's been moving from A to B. So I say that this statement is true. Question C. The osmotic pressure of a 1 molar solution of urea is the same as that of a 0.5 molar solution of potassium chloride. I say this statement is true because osmolarity of the 1 molar solution of urea is 1 times the dissociation constant of urea, which is 1. 1 times 1 gives you 1 osmolar as the osmolarity of the first solution. And for the KCl solution with a molarity of 0.5 molar, if we assume complete dissociation, then potassium chloride will have dissociation constant of 2. You multiply 0.5 molar with 2 to have 1 osmolar as the osmolarity of KCl. So the two solutions are isoosmotic. They have the same osmolarity. They have the same osmotic pressure. Question D. To make a 100 osmolar solution of magnesium chloride, 60 grams of salt are placed in a liter of water. So to solve this question, I'm going to solve the question similar to what we have at the beginning of the class. When we have the osmolarity of the solution, which is 100 osmolar, and then we have the volume of the solution, 1 liter. From here, we want to solve how many grams of salt that is needed to make this specific solution. And we want to test if the gram of salt that's needed to make this solution is similar or the same to 60 grams. If it is the same, then we say the statement is true. If the two numbers are far away from each other, then we say the statement is false. So from osmolarity, 100 osmolar, we can solve for the molarity. We use osmolarity, divide that by dissociation constant of magnesium chloride. If we assume complete dissociation, then 1 part of magnesium chloride will give out 3 parts of actively moving particles. So we will assume that the dissociation constant of magnesium chloride is 3. So the molarity of magnesium chloride will be 100 osmolar over 3. That gives you 33 molar as a molarity of magnesium chloride. From that, we want to solve for how many moles of magnesium chloride we need to make the solution. Since moles equals to since moles equals to molarity multiplied by volume of the solution, which is 33.3 molar times 1 liter, which is the volume of the solution, that gives you 33.3 moles as the moles of magnesium chloride. And then we can solve for the weight of the magnesium chloride that's needed to make the solution. We use the moles of the magnesium multiplied by molecular weight of magnesium chloride, which is 95.2 grams per mole. That gives you a very large number. That's over 3,000. The unit is gram. Okay, that number is very far away from 60 gram, which is listed in the question itself. So we say the statement is false. You can use other ways to solve the question, to do the calculation, to test the statement. One other method that I can think of is to take these into account, when you have 60 gram of magnesium chloride and when you put it into 1 liter of water, you can solve for the osmolarity of this solution and compare the final number with 100 osmolar. If it is close to 100 osmolar, then the statement is true. If it's very far away from 100 osmolar, then the statement is false. You can see that if you use 60 gram of magnesium chloride to convert this into moles, it'll be a very small number, less than 1 mole. And when you put it into 1 liter of water, that'll give you a very small number that's lower than 1 as the molarity of the solution. And if you multiply that by the dissociation constant of magnesium chloride, the resulting number is going to be much smaller than 100 osmolar. So this statement is false. Okay, so that is question number 6.